The event began at 14:37 Pacific Daylight Time on a Tuesday afternoon in late June, when ambient outdoor temperatures across the Las Vegas metropolitan area reached 43.3 degrees Celsius and relative humidity remained below 8%. At that moment, the building management systems serving a cluster of interconnected resort properties along a 1.2-kilometer section of Las Vegas Boulevard transitioned from standard cooling mode to what internal documentation later identified as Emergency Atmospheric Compensation Protocol, a subroutine designed to respond to detected contamination events or critical oxygen depletion within occupied zones. The protocol had been implemented across multiple properties following a 2019 update to the centralized BMS architecture, which consolidated HVAC control logic across resort complexes under a unified supervisory control and data acquisition system. The trigger condition was recorded in sensor logs as a simultaneous drop in oxygen partial pressure readings across 14 separate air quality monitoring stations, each sampling air composition at 0.5-second intervals within high-occupancy gaming floors, convention halls, and multi-story atriums. The readings, which later analysis attributed to a calibration drift in recently installed electrochemical O2 sensors manufactured to a revised specification, indicated oxygen concentrations between 18.2 and 18.7% by volume, below the 19.5% threshold programmed to initiate emergency ventilation response. Within 90 seconds of the first anomalous reading, the BMS issued command signals to 247 air handling units distributed across the affected properties, instructing supply fan variable frequency drives to ramp to maximum output while simultaneously closing economizer dampers to prevent mixing with potentially contaminated outdoor air and opening fresh air intake louvers to 100% position. The supply fans, each capable of moving between 35,000 and 120,000 cubic feet per minute, depending on unit size and application, began accelerating toward their maximum rated speeds. Concurrently, the protocol called for exhaust and return air systems to enter a coordinated purge cycle, but a logic error in the state machine governing mode transitions prevented the transmission of run commands to exhaust fan contactors across all but 3 of the 140 exhaust air handling units serving the affected zones. By 1441, differential pressure sensors located in main corridors, casino floors, and ballroom spaces began registering positive pressure relative to outdoor ambient conditions. The normal operating set point for these zones was maintained at plus 0.02 to plus 0.05 inches of water column to prevent infiltration of unconditioned outdoor air and particulate matter, a standard practice in large climate-controlled facilities in desert environments. Within 4 minutes of protocol initiation, recorded differentials exceeded plus 0.18 inches water column in perimeter zones and plus 0.24 inches in interior zones with limited pressure relief pathways. The rate of pressure increase varied by location based on volumetric capacity, air change rates, and the number and cross-sectional area of potential leakage paths, including door undercuts, elevator shaft penetrations, and building envelope penetrations for utility services. In the largest affected casino floor, a single-story space encompassing approximately 14,000 square meters with a ceiling height of 4.2 meters, the total enclosed volume of approximately 58,800 cubic meters was being supplied with air at a combined rate exceeding 680,000 CFM from 19 ceiling-mounted air handling units. With exhaust systems offline, the only significant pressure relief occurred through the building's revolving door assemblies, which maintained a small but continuous leakage area, and through gap tolerances around service doors in back-of-house corridors. Building automation logs recorded that static pressure in the main supply ductwork serving this zone reached 4.8 inches water column, well above the 2.5-inch design maximum, causing audible resonance in sheet mivel ductwork spans and triggering high static pressure alarms that were logged but not acted upon by the automated control sequence. The acoustic signature of pressurized duct systems, described in subsequent acoustic surveys as a low-frequency tone between 45 and 85 Hz with harmonic overtones, became detectable throughout occupied spaces. Fabric ceiling panels began to flex outward against their retention systems, and several acoustic ceiling tiles in corridor areas dislodged from their grid supports due to differential pressure across the plenum space. At 1446, the first documented attempt to exit through a main entrance occurred when hotel guests approached a pair of inward-swinging glass doors with a total leaf area of approximately 4.2 square meters per door. At an internal overpressure of plus 0.28 inches water column relative to outdoor conditions, the net force acting to keep each door closed was approximately 180 newtons, or roughly 18 kilograms force, distributed across the door's surface area. Standard panic hardware and commercial door closers are designed to operate with opening forces below 30 newtons under normal conditions to comply with accessibility standards. The individuals were unable to generate sufficient force to overcome the pressure differential, and the doors remained closed. Security camera footage time-stamped at 1447 showed similar attempts at 4 additional entrance points across the property cluster. Interior corridor doors, which opened against lower differential pressures because they connected pressurized zones to other pressurized zones rather than to outdoor ambient conditions, could still be operated but required noticeably greater effort than normal. The pressure gradient was not uniform throughout the connected structures. Areas with direct connection to outdoor conditions via operable windows, which existed primarily in older tower sections constructed before fully sealed curtain wall systems became standard, experienced lower pressure increases. A maintenance corridor in one tower section where a loading dock door had been left partially open maintained near ambient pressure, while adjacent sealed zones reached differentials exceeding plus 0.30 inches water column. By 1451, the internal pressure in the largest casino floor had stabilized at approximately plus 0.32 inches water column, representing a quasi-equilibrium between supply air input and unintended leakage through the building envelope, revolving doors, and other air pathways. This pressure level created a net outward force of approximately 940 newtons on a standard 0.9 by 2.1 meter inward swinging entrance door. Building occupants reported experiencing physiological effects consistent with rapid pressure changes, though the rate of pressure increase was significantly slower than that experienced during aircraft ascent or descent. Medical literature indicates that pressure change rates below 500 feet per minute of altitude equivalent are generally well tolerated by most individuals, while rates above 1,000 feet per minute can cause barotrauma in susceptible persons. The observed pressure increase of approximately 0.30 inches of water column over a 10-minute period corresponded to an altitude equivalent change rate of roughly 180 feet per minute, within the tolerance range for most individuals, but sufficient to cause ear discomfort in persons with eustachian tube dysfunction or upper respiratory congestion. Casino medical stations reported an increase in requests for assistance related to ear pressure and headache beginning in approximately 1505. The medical staff, operating within pressurized zones and experiencing similar conditions, initially attributed the complaints to environmental factors, including low humidity and high ambient noise levels, both typical of large casino environments. At 1512, engineering staff received multiple reports through internal communication systems regarding difficulty operating entrance doors. The engineering supervisor on duty accessed the building management system interface from a workstation located in a below-grade mechanical equipment room, which was experiencing its own pressure dynamics due to supply air from dedicated HVAC systems serving equipment spaces. The BMS dashboard displayed 247 supply fan units reporting 100% speed command and normal operation, but the overview screen did not automatically display exhaust fan status unless specifically queried. When the engineering supervisor navigated to the exhaust system status screens, the interface showed 137 of 140 exhaust fans in off status with no active fault codes, a condition that appeared to the operator as intentional shutdown rather than system malfunction. Protocol documentation reviewed during post-incident analysis revealed that the Emergency Atmospheric Compensation Protocol included a subroutine designated Atmos Purge 3, which was intended to coordinate supply and exhaust systems during contamination events. The logic sequence specified that upon receiving a contamination trigger, supply fans would increase to 100% output and fresh air dampers would open to 100% position to dilute contaminated air, while exhaust fans would simultaneously ramp to 100% to maintain space pressure within normal parameters. The error that prevented exhaust fan activation was traced to a state transition condition in the programmable logic controller code governing fan sequencing. The code included a conditional statement that evaluated whether outdoor air temperature exceeded 41 degrees Celsius, a threshold above which the economizer lockout function prevented the introduction of outdoor air during normal cooling operations to avoid thermal load penalties. When outdoor temperature exceeded this threshold, the economizer lockout flag was set to true, and through an unintended interaction with the emergency protocol state machine, this flag prevented the exhaust fan run command from being issued. The code had been tested during commissioning in March 2019, when outdoor temperatures were below 30 degrees Celsius, and the interaction between the economizer lockout condition and the emergency protocol had not been identified during functional testing or code review processes. The programming logic used a nested if-then structure, where the exhaust fan start command existed within a conditional block that evaluated the economizer lockout status, and the emergency protocol's priority override did not extend to clearing this flag before evaluating exhaust fan start conditions. As a result, the system continued to supply air at maximum capacity with no coordinated exhaust, creating the sustained overpressure condition. At 15:28, facilities management personnel attempted to manually override the BMS by accessing local fan control panels in mechanical rooms distributed throughout the affected properties. Each air handling unit was equipped with a hand-off auto selector switch that allowed operators to bypass BMS commands and operate equipment in manual mode. However, the supply fans were located in mechanical penthouses and rooftop equipment yards, while exhaust fans were distributed across multiple locations, including below-grade parking garage mechanical rooms, mid-rise mechanical equipment rooms, and rooftop exhaust plenums. The geographic distribution of equipment across multiple buildings and the requirement to access secure mechanical spaces with keycard access systems created coordination difficulties for the maintenance staff. Additionally, bringing exhaust fans online individually in manual mode while supply fans continued to operate at 100% capacity under BMS control resulted in only marginal pressure reduction because the supply air volume greatly exceeded exhaust capacity until a sufficient number of exhaust units were brought online. Pressure logs indicated that between 15:30 and 15:47, as maintenance personnel progressively activated exhaust fans in manual mode, the pressure differential in the main casino floor decreased from plus 0.32 to plus 0.26 inches water column, a reduction of approximately 19%, but still well above normal operating range. During this period, the BMS continued to register the spurious low oxygen readings from the faulty sensors and maintained the supply fans at maximum output. At 15:52, the facility's Director of Engineering made the decision to disable the Emergency Atmospheric Compensation Protocol entirely by accessing the supervisory control system and forcing the relevant control logic into an inactive state, then manually commanding all supply fans to reduce to 40% speed through BMS override commands. This action, combined with the ongoing manual activation of exhaust fans, caused internal pressure to begin decreasing at a rate of approximately 0.04 inches water column per minute. The physical effects of sustained overpressure on building systems became evident during subsequent inspection. Weather stripping and door gaskets, which normally seal against air infiltration under slight positive pressure, had been compressed beyond their elastic range in some locations. Several door assemblies exhibited permanent deformation of strike plates and latch mechanisms due to sustained force loading. In one second-floor corridor, a section of gasketed access panel covering a utility chase had been displaced outward by approximately 15 millimeters, allowing visual inspection of the pressurized plenum space behind the wall surface. Acoustic ceiling grid systems in several areas showed evidence of tile displacement and grid deflection, with 47 ceiling tiles documented as having separated from their supports.
The HVAC ductwork inspection, conducted 3 days after the incident, identified 12 locations where duct joints had partially separated due to internal pressure exceeding design specifications, though no complete duct failures occurred. Flexible duct connections between rigid ductwork and terminal devices showed stretching and stress marks consistent with pressure loading beyond rated conditions. In the main casino floor area, the fabric duct diffusers, which distributed conditioned air through porous textile material, had expanded to their maximum diameter and showed permanent elongation of fabric weave in multiple locations. Air velocity measurements taken at supply diffusers during the overpressure event, recorded by technicians using handheld anemometers, indicated discharge velocities between 950 and 1,200 feet per minute, compared to design values of 400 to 600 feet per minute for comfort cooling applications. These elevated velocities contributed to increased background noise levels, with sound pressure measurements reaching 68 to 72 dBA in occupied casino spaces, compared to typical levels of 58 to 62 dBA.
The pressure differential also affected elevator systems within the resort complexes. Modern elevator installations include ventilation requirements to prevent pressure buildup in hoistways during car movement, typically achieved through vents at the top of the shaft and pressure relief dampers at various floor levels. During the overpressure event, elevator cars moving downward within pressurized hoistways experienced reduced upward air resistance but created localized pressure spikes in the shaft below the car as air was compressed in the decreasing space. Conversely, cars moving upward compressed air in the space above the car while creating partial vacuum conditions below. These pressure dynamics were recorded by elevator monitoring systems as variations in door opening force and car leveling behavior. In 3 instances, elevator door operators required multiple attempts to achieve full door closure due to air pressure differences between the hoistway and the floor lobbies, both of which were pressurized but not necessarily at identical levels due to variations in supply air distribution and leakage characteristics. The elevator control systems logged these events as door obstruction faults, though no physical obstructions were present. Stairwell pressurization, normally maintained at positive pressure relative to building floors to prevent smoke infiltration during fire events, was reversed during the incident, with stairwells reading negative relative to the adjacent floor areas. This pressure reversal caused stairwell doors, which are typically equipped with automatic closers and latching hardware, to seal more tightly than normal, requiring increased force to open from the stairwell side. Several stairwell doors equipped with electronic access control systems experienced latch bolt binding due to the sustained pressure differential applying force perpendicular to the normal bolt travel direction. Environmental monitoring data collected during and after the incident provided quantitative documentation of the pressure event's progression and resolution. Differential pressure transmitters installed at 34 locations throughout the affected properties as part of the BMS control and monitoring system recorded continuous data at 15-second intervals. Analysis of this data revealed that the peak pressure differential of plus 0.34 inches water column occurred at 15:19, approximately 42 minutes after the initial protocol activation. The data showed spatial variation in peak pressure, with interior zones lacking direct outdoor exposure reaching higher differentials than perimeter zones with greater envelope leakage. The pressure decay curve following the initiation of corrective actions at 1552 showed an exponential decrease characteristic of first-order system response, with a time constant of approximately 8.3 minutes. By 1624, all monitored zones had returned to normal operating pressure range of plus 0.02 to plus 0.05 inches water column. Temperature data from the same period showed a decrease in space temperatures of 1.2 to 2.8 degrees Celsius across most occupied zones during the overpressure event, a consequence of the increased ventilation rate bringing in outdoor air that, despite its high dry bulb temperature of 43 degrees Celsius, had been cooled to supply air temperature of 13 to 15 degrees Celsius by the HVAC cooling coils before distribution to occupied spaces. The cooling plant, consisting of multiple centrifugal chillers with a combined capacity of approximately 28,000 tons of refrigeration, recorded increased electrical demand during the event as the cooling coils processed the elevated airflow. Power monitoring systems recorded a 23% increase in total HVAC electrical consumption during the peak overpressure period compared to normal operation at similar outdoor conditions. The incident documentation process included retrieval and preservation of BMS trend logs, energy management system data, access control system logs, and digital video recordings from security camera systems covering entrance areas and public spaces. The oxygen sensor calibration records were reviewed and compared against manufacturer specifications and installation documentation. Laboratory testing of the suspect sensors confirmed that 12 of the 14 sensors that reported low oxygen readings had calibration drift outside acceptable tolerances, with indicated oxygen concentrations reading 0.8 to 1.4 percentage points below actual values. The sensors had been installed 4 months prior to the incident as part of an indoor air quality monitoring upgrade, and the manufacturer's calibration stability specification indicated expected drift of less than 0.5 percentage points over a 12-month period under normal environmental conditions. The higher-than-expected drift rate was attributed to exposure to cleaning chemicals and elevated temperatures in ceiling plenum spaces where the sensors were mounted. The post-incident corrective actions included replacement of all oxygen sensors with units from an alternate manufacturer, implementation of a monthly sensor verification protocol using calibrated reference gas mixtures, and modification of the emergency atmospheric compensation protocol control logic to require confirmation from multiple independent sensor types before activation and to remove the conditional dependency between economizer lockout status and exhaust fan operation. The incident was documented in internal engineering reports and submitted to the facility's insurance carrier as a precautionary notification, despite the absence of injury claims or significant property damage. A review of relevant codes and standards, including ASHRAE Standard 62.1 regarding ventilation for acceptable indoor air quality, NFPA 92 regarding smoke control systems, and International Building Code provisions for means of egress, confirmed that while the building's normal HVAC systems met applicable requirements, the emergency protocol logic represented a control system failure mode that had not been anticipated during design or commissioning phases and was not specifically addressed by existing prescriptive code requirements for fail-safe operation of building environmental systems.